Just realised I was muted for the whole of that. So hello guys. Yeah, if you could all put your names in so I can tick you off on the register, that'd be great. So Jasmine here, Emerald, yep, Grace, Dom. Okay, so we're still missing a few people. Cool. All right, yeah. So today we're doing the next bit of normal distribution. This is actually the last bit of normal distribution, so that's good. And it's hypothesis testing. So I thought we'd take this opportunity to also summarize the the binomial hypothesis testing from um, earlier on. Why am I not here? Weird. I seem to have lost video. Yeah, loads of little technical difficulties today. I don't know what's going on really. Let's see if I can fix this quickly. Video capture source, webcam. Here I am. Cool. Why am I so big? Okay, let's try and sort this out. Cool. Right, we're all working again. Good. Okay, yeah, so we're quickly going to summarize everything we did on... Oh, I see. I'm on the wrong window. Yeah. So we're going to go over everything we did on binomial hypothesis testing from before. See you, Jake, you're in as well. Cool. All right. Okay, then, yeah, so binomial hypothesis testing, we are basically looking at testing the probability, seeing if the probability is accurate. So tests if probability is accurate. And the idea with that is if we've got a population and we're told the population of winning something is this, we can test that by taking a sample and seeing if what we get in the sample is statistically likely given what they've said about the population. So we did the example of McDonald's Monopoly. There's meant to be 1/5. If we do a sample and we win less than that, we could test whether our value still could be coming from the same population. And if it's really unlikely that our sample represents the population, then we can we can state whether the hypothesis is true or false. Yeah, Ed, I've got you ticked off. So that's all fine. Okay, so for example, we said like the chances of winning a prize. Cool. Rob, yeah, I got you here. Both of you guys are ready. Okay. So next up, we're looking at the normal distribution, and what we're testing with a normal distribution is the mean. So same idea. Instead of testing the probability this time, we're going to be testing the means. So for example, if we had I don't know, like a phone company say our battery will last 10 hours on average. If we bought 20 phones, on average it lasted less, we could test to see whether the mean of our sample could be coming from the whole population. So the nice example for that one's e.g. phone battery is something hours. Same idea. Someone says a statement and we're trying to test whether the mean could be coming from the actual population based on our sample. And the last one, correlation, which I'll put on this slide now, but we won't be doing this until next week. tests if the correlation coefficient of a sample represents the coefficient for the population. So in all of these cases, we're taking a sample, doing some stats on it, predicting some stuff, and seeing if our sample could be from the population that people are claiming it is. So either it's someone claiming the probability of winning is something, and we're testing if our sample of wins matches. Someone's claiming the mean of something is value, and we're seeing if our sample mean matches. Or someone's claiming the correlation is something, and we're seeing if our sample correlation matches. In each case, start with population. We're taking a sample to test whether the claim is likely. And that's what hypothesis testing is. Okay, so yeah, we're going to be looking at normal hypothesis testing. So I thought I'd use this phone example. So apparently the best phone at the moment is the iPhone 11 Pro, and it should be because it costs thousands. For streaming, it says it will do 11 hours. So the population should have a mean. Let's use battery for phone life. Battery should last. Normal distribution, mean is 11. Standard deviation, I've gone for like 1.5. So we're saying the battery of a phone, all of the phones, all the iPhones, should have a mean of 11 if that's what they're claiming, and roughly, I said about 1.5 hours for the standard deviation. So if I bought 10 iPhones, which I can afford now because I'm a big streamer, so if I bought 10, and if all the other Maths YouTube channels bought 10 as well, so like Exam Solutions buys 10, and all the other ones, Dr. Frost buys 10, and Physics and Maths Tutor, they all buy 10, so we've all bought 10 phones each. We work out the the average lifetime of the battery when you're streaming something. We could then find the mean of all of our averages, and we could test whether that mean could be coming from the overall sample mean. Because the means of all these battery lives should also be normally distributed. If the original battery life is distributed normally, the means of our sample should also be distributed normally. So we can say if B is the battery life, we can say the sample means B should also be normally distributed, should also have a mean of mu, or 11 in this case, and then we should have sigma squared. Now the difference is, because our sample's a lot smaller than all the iPhones in the world, we have to change our standard deviation. Remember, standard deviation talks about the spread of the data. If we've only got, what I said, 40 phones, we're not going to have as many phones to have that bigger spread. So we need to divide our variance by the number of phones we have, divided by n. So that, we say, is the distribution of sample means. And that's what we can use to test whether a claim about a mean is true or false. Right, has anyone got any questions so far? Because it's kind of confusing whenever you do a hypothesis test until you start kind of practicing it. So if we take a sample, we can take lots and lots of different samples from a population. The mean of each sample should also be normally distributed, and that's given by this equation over here. There you go. But the only difference we have to make is we have to divide the variance by n, so we kind of squash the spread, so it still should fit the original distribution. All right, so we're going to try this and do a quick test on the iPhone battery. So the original battery life again, B, normal, 11 and 1.5 squared. We said that the means should also be normal, should still have a mean of 11, but the spread will be a bit smaller. It'll be that divided by n. So, if I buy 10 phones, and my mean battery life is 10 hours, can I complain? So that's what we're trying to test. Okay, so just to demonstrate this, we're going to do an easier test where we just find the probability. So my hypotheses are these. H0 mu is 11. H1, the mean is less than 11, which is what I'm trying to test. So I'm going to plot a graph of my sample mean distribution. Sorry, guys, I think I have hiccups today. To draw a yeah, definitely draw a normal distribution for my sample means. So the mean should be 11. I found that my mean was actually 10. So we're trying to find out if this probability is likely to happen. So we're trying to find this area. So we're doing a one-tailed test. Cool. So I can bring up the calculator. Which zooms everything in for some reason. So let's fix that quickly. Cool. So on the calculator, we are going to do a normal distribution. We're going to try and find the probability. So statistics, exit the distribution, normal distribution. We want the probability, so it's a cumulative distribution. Lower value 0, upper value 10. Sigma is going to be 1.5 squared divided by n. Well, I've bought 10 phones, so I need to do 1.5 over square root 1.5 over root 10 to get 0.47, and my mean is 11 because that's what we're going to test. So if I plot this, we see based on the sample means, the probability of me finding a mean battery life of 10 is 0.017. So in other words, 1.75%, which is quite unlikely. So if we were testing, yeah, I have hiccups. Thank you, Ed. So we are testing. What was I saying? We 1.75%. So if we had a hypothesis test with maybe a 5% significance level, that would be in the significant area. So it's likely 5% significance level. So this would be critical. So in this example, I would have a claim to complain about the battery life. So just to kind of explain that again, because I was hiccuping the whole way through. There's a claim that phone battery lives last 11 hours, and we know the standard deviation is 1.5. Of all the samples of anything you take, the means of all the sample should also be normally distributed. So we've got a normal distribution for B for our mean of the battery life, which should have the same mean, and the spread will be 1.5 squared divided by n, where n is the number of items in your sample. Dom, it should be 1.5 over root n. Neither of the things you said, because remember this is the variance. So sigma is going to be 1.5 over root 10. Thank you for asking though, but yeah, so we need to square root all of this. We need to square root the top, easily done, and we need to square root wherever n is, so 10 becomes square rooted to root 10. So then I plotted the distribution for the means, which is here. The mean should be 11. The mean of the mean should be 11. We found our mean was 10. What's the chance of that actually happening? 1.75%. So because it's 1.75%, that's quite rare. We can then say, well, we're going to accept H1 and refuse H0. So accept H1. Cool, right. It's not always that easy because normally the better way to do these is to find critical regions. Rather than find the percentage, you'll be given the percentage and asked to see if a value is in the critical region. So we're going to try doing it that way. I'll just leave this here for a second in case anybody does have any questions. And I think I'm going to go get some water. So have a quick look through this, guys. Let me know if you've got any questions in a second. Cool. All right. Any questions then? No? Cool. Right. Moving on then. So this is a more common style of question. So in this one, we are asked to actually find the critical regions. So a machine produces bolts diameter D, where D has a normal distribution of mean 0.580 and standard deviation 0.015. So let's turn that into a distribution. So D, normal distribution, mean of 0.58, and a standard deviation of 0.015, which I'm going to write squared because that's the variance. So to do this one then, we need to find the critical region. So machine is serviced. So you've got this machine making bolts, which is then serviced. And they've taken a sample of 50 bolts to find the mean to see if the mean has changed. Because if the mean has changed, their machine is no longer making the bolts correct. So we're trying to test whether the mean has changed from 0.580. So the distribution of bolts after the service is still normal and has a standard deviation of 0.15. So the standard deviation is the same. So we're going to do a test at the 1% level, stating our hypotheses clearly. So to state my hypotheses, first of all, H0 is going to be mu is still 0.58. So again, null hypothesis, nothing has changed. H1 is going to be mu is not equal 0.58 because all they've said is has it changed. They haven't said has it increased or decreased, they just said it's changed. So this is going to be a two-tail test. Cool. Okay, so back to the question. So we're looking at the 1% level. So if I sketch my distribution, we're trying to find out what these critical regions are. If it's 1% in total, we need to split that up for each tail. So we're going to have 0.5% or 0.005 there, and we'll have 0.005 there as well. Cool. All right, last bit is to write down my distribution, then we can actually do some calculations. So my mean distribution is going to be D mean, and mean should be the same, and our standard deviation is going to be 0.015 over our sample is size 50. So I'm going to put 50 in there. Cool. All right, so part A is asking us to find the critical region. So all we need to do for the critical region is to work out what these x values here and here are, these two x values. So we're going to get the calculator out. We're going to put in our probability 0.05. We're going to put in our standard deviation, and we'll put in our mean as well. Actually, do we need to? Yeah, okay, we can't use this yet because they've told us the 50 in part B. So for part A then, if I get rid of that for a second, we will be coming back to that. But for now, just so I've got some space, we're going to do a Z calculation using the standardized normal distribution so that we can find these without knowing the bit about 50 later. So we're going to find the Z values of the critical region. So if I bring up the graphical calculator, all right, and we're going to do distribution, normal distribution, inverse normal because we know the probabilities. You can do either tail because the percentage is the same for each tail, so it doesn't actually matter which way round we have it this time. So I'm just going to copy myself back over. I'm lost in that other window. There we go. So yeah, we're going to put in 0.05. We can put it in as lower or upper as the lower or upper tail, so it doesn't actually matter because both the tails are the same. So I'm going to go left for this one. Area 0.05. Sigma we're going to put in 0.015. Oh, I'm sorry. Sigma is going to be 0 because we're talking about the standardized normal distribution. And sorry, sigma is 1, and mu is 0 because we're finding z. So hit execute, and we get z is minus 1.64. So z is going to be plus or minus 1.644. Okay, but what we're going to need to do now, though, is to code our z value to find out what the actual critical region would have to be. So we're going to use our distribution in order to code this. So we've got a sample of 50 bolts. Let's write that thing back up that I had just now. D normal 0.58, 0.015 over 50 squared. So we're going to code our Z value into a D value using our standard, sample means. So we're going to use the equation as we had it before, Z equals X minus mu over sigma. The only difference now is sigma isn't going to be sigma. Sigma is going to be sigma over root n because we got to bring that 50 in. So if we try and solve that, let's make some more space up here. We can do 1.644 equals x minus 0.58 over 0.015 over root 50. So if you get a calculator out, we can now solve that. So 0.015 divided by root 50 times by 1.644 plus 0.58. And we get an upper D value of 0.583. So slightly more than our mean. And our lower value will be Same thing but with negative z. And then plus 0.58 to it. So 0.5, 0.577. Okay, so those are our critical regions. So I go back to a sketch. If I do one up here, we found that the value here where there's 0.5% there is 0.583. The value here where there's 0.5% is 0.577. So those are our critical regions. Now we can actually look at the part B, which is the hypothesis test. So the mean diameter is 0.587. So is that in the critical region? So 0.583 is here, 0.587 will be over here. So yes, that is critical. So we can say 0.587 is critical. Therefore, accept H1 and the diameter has changed. Cool. Everyone okay with that? So we found the critical region by finding the 5% bit for Z. We then coded Z using sigma to find our critical values. And then we had a look to see if our value was in the critical region. It was, so we reject H0 and accept H1 and then state, well, the diameter has changed. So you got to link it back to the question as well. All right, anyone got any questions about that? Cool. All right, I would like you guys to try one yourselves. So you guys are going to try one about water voles. So here you go. I'll just move this down very slightly. There you go. Cool. Could you guys try this? I'll give you a couple of hints for it. So part A is like a basic normal distribution question. Part B is a binomial question plus normal. And then part C is a hypothesis test. Oh, Melissa, you have a good point there. I might have made a mistake there. 0. Where did I write it? It'd be in the calculator. Yeah, I have made a mistake. Oh my god, that should be 0.05. So if you guys want to change that, that might affect our Z. Well spotted, Melissa. I think I did that this morning as well. 0.05. 0.05 is what I meant. So yeah, Z should actually be... Okay, that might change things then. Let's quickly redo this then. Just the last bit. So Z there should be minus 2.576 times by... So we do get a much smaller value for our lower one. So yeah, it should actually be 0.74 there. So if you guys could change that digit to a 4. And the upper one, 2.576 times by 0.015 over root 50 plus 0.58, 0.585. It doesn't actually make much difference, but my decimal places were out by 2. So yeah, 0.574 and 0.585 were my critical regions. Well spotted there. So be careful with your percentages. Um, yeah, is everybody right with that? So yeah, it would still be critical, still accept H0. The only difference is these two numbers should be different. Okay, let's try this waterfall one then. So we got normal, binomial plus normal, and then a normal hypothesis test at the end. Rob, which bits, Rob? All of it, or just a bit? Everything I just said. So problem was I put into the calculator 0.5%. I used 0.05. 0.05% should be 0.005. So that's what we should have used. Which slightly changed our answers by a couple of decimal points. It doesn't affect the result, but it does affect your answers. So be careful when you're typing in percentages that you don't miss out a decimal point, like I just did. That okay? All right, let's move because we'll address this in the next question anyway. Cool. All right. So yeah, this is worth 10 marks. I'm gonna give you guys 12 minutes because these are quite tricky at first. If you need help, please just comment and I will give you some hints. But I'll start clock. 12 minutes. Give it a go. Comment your answers when you think you've done it. Oh, oops. And we'll see how you get on. Sorry guys, everything's a bit broken today, including my voice for these hiccups. So there you go. And it seems the timer's broken. Cool, there you go. 11 minutes. Give it a go. Anyone need any help? So answers for the first one should be 136.48 and then 0.0129. And we'll go through the hypothesis test one in a minute. But so 4 more minutes, guys, or 5 more minutes. Let me know if you do need any help. Part B was 0.0129. Cool. All right, let's go through these then. So the first one, which is a regular normal distribution question. We're told these water voles are distributed with a standard deviation of 12, and we're trying to find the mean. Okay, so mean is unknown. We know that's 12 squared. So we need to use the z distribution to find mu. So number z equals x minus mu over sigma. Okay, and we're told 2.5% have a mass greater than 160, so that's 0.025. So the idea is find z, and then we can code z back into x, to find mu. So if I bring up the calculator, our tail is to the right, although if you're finding z, it doesn't really matter. Area is 0.025, and the mu is 0 and sigma is 1. So you get 1.959, or z equals 1.96. Cool. So we can then use our z value with the equation up there to try and find mu. So 1.96 equals x, or x was 160 from there, minus mu divided by sigma, which was 12. And if we rearrange that, we get mu equals 136.48. Cool, which is our mean. So let's write that up here, 136.48. All right, part B. What did Molly say? Can you not use n plus 2 theta equals 160? Could you? 2.5. Yeah, you could actually, because 2.5 is either side of the table. Yep, that would be a really nice way of doing it as well. That would work absolutely fine. Okay, part B then, binomial distribution. So 8 voles are chosen at random. So we're trying to find the number of moles that have a mass greater than 150. So we want our number is going to be 4. Oh, sorry, 8 is our number in the sample. The probability in the sample we don't know, and we're trying to find the probability n is greater than or equal to 4. So in order to do this, we need to find out what that probability is. So we're going to need to do a normal distribution in order to find the probability that a vole has a mass greater than 150. So we want to find probability x is greater than 150, and then we're going to write that in there to do our binomial with. So we know all the bits now for this normal distribution. So we just worked out this is 136.48. So I can just type this into the calculator. So if we go back, put the tail to the right because we're greater than 150. We're not looking inverse now though. We're going distribution, normal. Uh-oh. Maybe the iPad's broken again. It has been doing that a lot. We'll see if it comes back. Maybe. So we've typed this back in then. So NCD, our lower value was 150. Upper value, let's just put in a big number, 20,000. Sigma is 12 and mu is 136.48. Cool. If we draw it, we get our probability as being... have I typed something in wrong there? Oh, sigma's not 1. It should be 12. Cool. There we go. So probability 0.1299. Come on, iPad. Okay, that might work. Okay, so then we're going to use a binomial distribution in order to work out the probability n is greater than 4. So bring back the calculator, back to distribution, binomial this time, B, C, D. Our lower is going to be 4, upper is going to be 8. Number of trials is 8, and there's my probability already typed in. Calculate, and we get 0. The overall probability 0.129. 0.0129. Cool. Everyone right with that? What have we got in the comments? Molly said, okay, you did it with n plus 2 sigma. And you got 160. Yeah. I think that would be fine. You've basically kind of skipped out the Z section. Yeah, if we rounded less, or if we rounded more accurately, we'd probably get the same as you. So that would be fine. You'd get error carried forward on that one. All right. So last bit for this one is the hypothesis test. So, and this is on a completely different species, so you can get rid of everything we've done so far. Molly, I'll check that in a minute, but it should be right. I don't see why you'd get that wrong for using a different correct method in part A. So they'd probably have a set of answers in that one. But I will check. All right, part C. So water rats have a mass n, so we're using n is a normal with mean of okay, so our sample mean is 875. So that's our test statistic. If you keep reading, the mass of all the water rats should be 860. And our standard deviation is 85, so 85 squared there. So that's our normal distribution for their mass. The sample mean distribution, n bar, will be the same mean, and then 85 squared over, and we need to divide it by 15 because that's our sample size. Okay, state our hypotheses. So we got h naught p no mu even equals 860. H1, we're testing whether it's different, so it's going to be mu is not equal to 860. Okay, we're using a 10% significance level, which gives me 5% for each tail. And we're going to try and find the critical regions and see whether a mass of 875, which is here, lies in these critical regions. Okay, so I can bring the calculator back. And this time we're looking at normal, inverse normal. We can do either tail because the percentage is the same each way. So if we do the left tail first, the area 0.05, we know sigma is going to be 85 over square root of 15, and mu is 860. So go to execute, and we get 823 as our lower value, which I'll add to the graph there. So 823.9. Our upper value, same idea. On this calculator, I can just change my tail to right. On the class Wiz, it's a little bit more involved than that. You're gonna have to do some more workings, or you could find Z first and work it through that way. Hit execute, and we get 896.1 if we round. So those are my values. Okay, so if we compare these then, so our test statistic was 875. So 875 is not critical. You can see it's way off the critical region. So not critical. Therefore, accept H0, and we can say the masses of the water rats is likely to be 860. Well, there is evidence to suggest the mass is not different to 860. All right, any questions? Sorry about all this hiccuping, guys. Wait and see if anyone's got any bits they want me to go over. No? Okay. Cool. I want you guys to try this one. It's should be pretty straightforward. There we go. So 4 marks. You got daily wind speeds. Sample of 25. It's a pretty straightforward hypothesis test though. So 4 marks. I'll give you guys 4 minutes to do this one. Thanks, Jack. Sorry, I keep doing that. Um, yeah, so we'll write down what we've got. So wind speed W, normal distribution. 3.1 is our standard deviation. In our sample mean, we're going to have 3.1 and 25. Just rewatch it, Elizabeth. It's still going to be online. Still going to be online, and I will be redoing it tomorrow morning. Second lecture if you do want to do it again. So yeah, 3.1 squared is our standard is our variance. Mean of the sample is on actually, Rob. Mean of the sample is 12.2. If you keep reading, the mean wind speed is 9.5, and we're going to use that in our sample mean as well. Cool. So there we go. Those are those two. We want to find 2.5% significance level, whether it's greater than. So it's a one-tailed test. There's our mean. We're looking for 2.5%. So we're trying to find this critical value. Okay, dokie. So if we go to our calculator, we're going to go greater than 2.5%, put in our sample standard deviation and our mean. So remember, sigma is going to be 3.1 over root 25, which is 5. So I bring back the calculator. Go back, and we're going to go tail to the right. Area 2.5%, so 0.25. Yep. Sigma is going to be 3.1 over 5. And mu is going to be 9.5. Cool. Go to execute. And that tells me the value is 10.7. So that is my critical value. So my critical region is anything greater than 10.715. What's our value? We're trying to test 12.2. So 12.2 is critical. What have I forgotten to do though? If you guys could comment. I don't think I'm too far behind with lag today. What have I forgotten to do with this question? Why have I lost 2 marks? Anybody? Secret code? No. This specific. Why have I lost marks in this question? So hypotheses, well done, Jack. I needed an excuse for the Cool, well done, Jack. So yeah, we need to state some hypotheses. So could you guys try and write what the hypotheses should be? Can you guys put what you think we should write for these? So H0 and H1. So yeah, H1 is mu equals, what was that? 9.5. Mu is greater than 9.5. So we're going to reject H0, accept H1, 12 is critical. So the wind speed is likely to be more than 9.5. Cool. So nice easy one there. Pretty straightforward. All you have to do is literally just the hypothesis test. Cool. Okie dokie. Okay, we're gonna do one more question. So if you guys could try this one. There you go. So I'll talk you through the parts again, and then you guys can try it. So climbing rope produced by manufacturer, and it's known that 1 meter lengths have braking strengths that are normally distributed with a mean of 170.2 and standard deviation 10.5. So part one is a normal question. Part two is a um, normal question as well, but using the means. And then part C is a normal hypothesis test. Okay, give it a go. Part B is a bit tricky because you're doing a standard question, but with the sample mean distribution. You're not actually doing a hypothesis test. You're just doing some standard normal stuff with the mean distribution. See how you get on though. So this is an 8 mark question. Give you guys 8 minutes, and then we'll go through this, and that should bring us nicely up to the end. Please comment if you get stuck or you don't know what to do. If you don't know what to do though. So 8 minutes on the clock. See how you get on. Thank you. Thought I had it then. Nope. Yeah, so we're going to use B for breaking strength. It's a normal distribution with a mean of 170.2 and a standard deviation of 10.5 squared. Okay, 1 meter length of rope chosen at random. Find the probability it will have a breaking strength of 175 to the nearest kilogram. So we're trying to find the probability that B is to the nearest kilogram. We can use 174.5 to B to 175.5, and that's the range that would give us 175 to the nearest kilogram. So if we bring the calculator up and we're going for a distribution, normal distribution, cumulative, 174.5 to 175.5. Sigma is 10.5 squared, or it's not squared. Mu is 170.2. Sketch it. And there we go. So 0.0342. Cool. Hopefully everyone's right with that. Cool. All right. Next bit then. So one random sample. Find the probability that one random sample of 50 will have a mean breaking strength of more than 172.4. So it's the same kind of question, but instead of using the standard normal, we're going to be using the sample mean normal instead. So we still have 170.2. We've now got 10.5 squared over our sample 50. But other than that, it's the same thing. We're trying to find the probability that it has a mean of more than 172.4. So probability that mean is greater than 172.4. So back to the calculator. Remember to square root your 50. Come on, laptop. Everything's breaking. Cool. So my lower is 172.4. Upper, put in a big number. Sigma is 10.5 over square root of 50. And mu is 170.2. Draw it. There's our region. So we're looking for 0.06. Yeah, 0.069. Cool. Right, so that's the first two bits. Last bit is a hypothesis test. So if I clear the screen there and move the question up. So a new component is added to the ropes, and we're going to see if it increases the strength. Okay, so we can write our distribution again. I'm just going to move this one up. And we're going to try and test hypothesis test whether the strength of these ropes has increased. So our null hypothesis, H0, is going to be H equals 170, not H, mu. And H1, mu is not. Oh wait, was it less? Yeah. Increased. So mu is greater than 170.2. Cool. All right. Okay, so we're going to do our test, see if we can find our critical region, and then see if 172.4 is bigger than it. So we're looking for 5%. So if I bring up the calculator and type it all in. So we're doing inverse normal again because we know the probability. So distribution, normal, infinite, tails to the right, area 0.05. Sigma is, I'll type it in again just in case, 10.5 over square root of 50. Mu 170.2. And let's have a look. So we get 170.3. Really? Let's double check that quickly. 0.05. Mu, quite small. Cool, okay. Yep. So our value there, 170.32. Yeah. I think that's alright. Standard deviation was wrong, really? What have I done? Where's my calculator? Standard deviation, how did I type it in? 10.5 divided by square root 50. Yes, it was. Well spotted there. Cool, go to execute. Yeah, 172, that makes a bit more sense. 172.64. Okay, so our value 172.4, that is not critical. It's just outside of the critical region by about 0.2. So yeah, it's not in the critical region. So it is not critical. Therefore, reject H1. The rope is not stronger. If we were doing a 10% significance level, probably even a 6%, any more percent to include 0.4. But because we got that 0.2 out, then we're not gonna be able to confirm their testing. Cool. All right. Has anyone got any questions? That's pretty much it for hypothesis testing with the normal. We're going to do a bit more practice on Friday and then move on to the last topic next week. Cool. Any questions, guys? Cool. If there aren't any questions, I need to show you guys how we're going to do homework assignments. So if you log onto Moodle, here you go. And I suppose I should hide password. Yeah, so we have to set you guys homework assignments still because we don't know what's going to happen with grades. So if you go to Moodle, scroll all the way down to the bottom, you can see the new assignment and skills check column. So I think you guys are on assignment 24. So click on there. There's a skills check. You need to upload a photo of anything you struggle with on your assignment. Don't write anything in this box. This is just an uploader. And you're going to answer your questions in these bits. And it will tell you straight away if you got it right or got it wrong. And it will send it to me. And then I can look through your workings and give you any points for correction. So if you guys could keep, I know it's a pain, but you haven't got much that you can do at home. So if you could keep working with the assignments and keep revising. Um, and there's your skills checks. So there's only like 6 left, so it shouldn't take too long. You should have done assignment 24 already because that was due the day that I started self-isolating last week. So are we going to use as a reference for grades? We're still a bit iffy about what's going on. I think my next meeting with the maths team is next week, so next week we'll probably decide what's actually happening. We've had a bit of guidance from college, but I think we need to get together as a team before we decide anything concrete. So I would keep doing things, keep revising. Yeah. Sorry, I can't say more at the moment, but soon everyone will work it out. But you need to know this stuff. Let me just have a quick check. I haven't thoroughly read through the email yet. Just let it load a sec. Am I in? So it's really slow while I'm streaming. Come on. Sorry guys, is coming. Where is it? Yeah, okay. God, it's a long email. Just give me a sec. The calculated grades process will take into account a range of evidence, including, for example, non-exam assessment, mock results, and the approach will be standardized between schools and colleges. Ofqual is working urgently with the exam boards to set up proposals for how this process will work, and we'll be talking to teachers' representatives before finalizing an approach. To ensure that this approach is taken as fair as possible, we're making our views clear at national level with our expectation that any grading system, when finalized, will reflect the same outstanding results in previous years. So it sounds like there'll be a calculation of your grades based on what we say about you, what your mock results were, possibly what you predicted, and it sounds like that will be standardized to what the college normally gets in terms of its results. Da, da, da. So yeah, we will be taking individual circumstances into account. Obviously, the assessment needs to reflect students' work over an extended period. Uh, but yeah, so we need to decide as a maths department what we're going to do. Does that kind of make sense? So it'll be, well, if you don't feel that, Ollie, you're going to have to show that you've progressed since somehow. I'm not sure how students are meant to do that yet. Yeah, basically, I would keep revising because even if you get a bad grade, if you disagree with the grade you get given, you are allowed to do a retake. By the sounds of it, what does it say early next year? So if you disagree, you can take an exam next year to prove that you deserved a better grade. Yeah, pupils who do not feel their calculated grade reflects their performance will have the opportunity to sit an exam as soon as is reasonably possible after schools and colleges open again. We don't know when that's going to be though. And so, yeah, so part of it is it sounds like we're going to have some say in your grades. Um, what's that, Ollie? It was just a bad exam though. We can also appeal the grade before. What do you mean? Yeah, there's a bit of delay here. So I think it's going to be based on a number of things. As a maths department, we haven't sat down to discuss how we're going to do it because obviously, yeah, once you've been given a new grade, you can appeal the grade you were given and do a test to prove otherwise. I don't see it saying anywhere about having to redo a year, Rob. I haven't seen that. I don't know. That's all I've got is what's in that email. I assume there'll be some more guidance once the government has finished speaking to Ofqual, who sort out all the exams. But yeah, there's a lot of unknowns still in that statement. So as far as I'm concerned, we should be kind of going ahead as normal. And as soon as Maths Department and Truro College have decided how we're going to assess you guys and what our criteria are going to be, I will let you know. And if you're worried, then we'll try and think of ways that you can prove improvement since the mock exams. Um, yeah, hope that clarifies. I mean, I don't feel like it's very clear, but that's what we have at the moment to go on. Um, they want to stress that you won't be judged on the work we're currently doing because obviously some students might be disadvantaged by not being able to access the internet or whatever. But some of you will probably want you to be judged on this work because you might have used mock exams test to see where we were. What do you mean, Ollie? Not really sure what you mean by that. If you guys want to go, you can, because that's the end of the lecture. We'll be finishing this off on Friday. There's your skills checks. If you do want to stay to chat about things, I'll just do it in the chat now because it's a bit faster. So yeah. Anyway, thank you for watching. I will stay to answer any questions in the chat. So otherwise, see you guys on Friday. I will be repeating this tomorrow morning, and my hiccups have gone, so hopefully, yeah, if you want to watch again tomorrow, it will probably be a better version of this lecture.